This black hole is bigger than our entire solar system when astronomers first encountered the data. Their reaction was not excitement, but suspicion. Something in the numbers felt wrong. The mass estimates were too high, the size too extreme. The energy output too vast to fit comfortably within existing models of how the universe works. Teams working independently reached similar conclusions. And each time the response was the same. Check the calculations again, then check them a third time. Assumptions were revisited, instruments recalibrated, alternative explanations explored. In science, extraordinary claims demand extraordinary scrutiny. And this claim appeared to sit far beyond what gravity was supposed to be capable of assembling. Yet the numbers refused to go away. Every method pointed in the same direction. The object was not an artifact of faulty measurement or statistical fluke. It was real. Light from it had been traveling toward Earth for billions of years, carrying with it unambiguous signatures imprinted by the laws of physics themselves. Spectral lines showed immense velocities. Luminosity measurements implied staggering power. Gravitational constraints demanded an object of almost unimaginable mass. The more carefully the data were examined, the clearer it became that this was not a theoretical curiosity or a speculative extrapolation. It was something the universe had already built. What made this discovery unsettling was not just its size, but what that size implied. Gravity, as understood through general relativity and decades of observation, follows well-defined rules. Black holes grow by feeding, but that growth is limited by time, fuel, and the violent radiation produced as matter falls inward. There are natural brakes built into the process. Push too hard, and the system pushes back. Radiation blows material away. Growth slows. Yet here was an object that appeared to have raced past those constraints, assembling a mass so enormous that it strained the upper edges of plausible cosmic history. This forced astronomers into an uncomfortable position. Either something about the early universe was far more efficient, more violent, or more cooperative than expected, or the models themselves were incomplete. Neither option was reassuring. Modern cosmology rests on a framework that has been tested across scales ranging from subatomic particles to the structure of the observable universe. Discoveries like this do not overthrow that framework outright, but they expose cracks where new understanding must eventually emerge. The disbelief was not emotional disbelief, but methodological caution. Scientists are trained to distrust surprising results, especially ones that appear to rewrite boundaries. They asked whether the object might be multiple sources blended together by distance. They considered whether dust or lensing effects could be artificially boosting its brightness. They questioned whether relationships used to estimate mass might break down at such extremes. Each possibility was examined and found wanting. Independent observations across different wavelengths reinforced the same conclusion. The monster remained. What made the situation even more unsettling was how unambiguous the evidence was. This was not an indirect inference built on a single fragile assumption. Multiple lines of reasoning converged. The sheer brightness demanded a colossal engine. The variability of that brightness constrained the size of the region producing it. The width of emission lines revealed the speed of gas whipped around by intense gravity. Together, these pieces formed a coherent picture, and it was not one that could be easily dismissed. There is a moment in science when doubt transitions into acceptance. Not because the result feels comfortable, but because resisting it requires increasingly implausible alternatives. This discovery crossed that threshold quietly, without headlines or drama. As researchers published cautious papers filled with error bars and caveats. But beneath the restrained language was an implicit acknowledgement. Nature had produced something operating at the extreme edge of what theory allowed. The cognitive dissonance arises from the tension between expectation and reality. On one hand, the equations of gravity are elegant and predictive. On the other, the universe seems determined to explore every loophole those equations permit. This object sits precisely in that gap. It does not violate known laws, but it exploits them to their absolute limits. It forces a re-examination of how quickly structure can form, how efficiently matter can fall inward, and how violent the early universe may have been. What elevates this discovery beyond a record-breaking curiosity is its timing. The light we see today began its journey when the universe was still young, when galaxies were assembling and chaos was common. That this object already existed then implies a sequence of events that unfolded with breathtaking speed. It suggests that under the right conditions, gravity can act with ruthless efficiency. Building giants before the cosmic clock seems ready for them. This is why the discovery carries such weight. It is not merely the largest of its kind, but a stress test for our understanding of cosmic evolution. It asks whether our timelines are too conservative, whether our assumptions about early environments are incomplete, and whether other such giants may still be waiting, unseen, in the depths of space. Each confirmed detail raises new questions, and each question leads further from comfortable certainty. The universe does not offer explanations up front. It presents facts encoded in faint, ancient light, and leaves interpretation to those willing to confront uncomfortable implications. In this case, the implication is clear. Gravity, given time and opportunity, can create objects that feel almost unreal, even to those who study them for a living. This is not a hypothetical boundary pusher imagined on a chalkboard. It is an object that exists, that shines. And that quietly informs us that the cosmos is capable of more than we expected. This realization reframes everything that follows. Before understanding how such an object works, or what happens near it, or what it means for the future of astrophysics, one must first sit with the fact of its existence. Against expectation, against intuition, and against comfort, the universe has already done the impossible. To understand what it means for a black hole to be bigger than our entire solar system, we have to begin somewhere familiar. Not with galaxies or exotic physics, but with the space we already call home. The solar system is not just the sun and a few planets huddled nearby. It is a vast, layered structure extending far beyond what most people imagine when they picture planetary orbits. At the center sits the sun, a sphere of plasma so massive it contains more than 99% of all the mass in the solar system. Around it, at increasing distances, orbit the inner rocky planets. Mercury circles close, completing a year in just 88 days. Venus follows, then Earth, then Mars. These worlds feel spread out to us, but on a cosmic scale they are tightly packed, clustered within a region that light can cross in minutes. Beyond Mars lies the asteroid belt, a broad but sparse ring of rocky debris left over from planetary formation. Individual asteroids are separated by vast distances, yet this region marks an important boundary. The transition from the warm inner system to the colder realms beyond. Past it, the gas giants dominate. Jupiter, with its immense gravity, reigns as the largest planet, followed by Saturn with its iconic rings. Then Uranus and Neptune, pale and distant, orbiting in the frigid outer dark. Even here, we are still only partway through the solar system. Neptune's orbit marks the edge of the classical planetary zone, but far beyond it lies the Kuiper belt. This is a sprawling disk of icy bodies, remnants of formation, extending outward for tens of billions of kilometers. Pluto is not an outlier, but a representative member, one object among countless frozen worlds circling slowly in the cold. Pluto's average distance is about 40 times farther from the Sun than Earth. Light takes over 5 hours to reach it, yet even Pluto does not define the true scale of the solar system. Beyond the Kuiper belt, the Sun's gravitational influence continues into a vast spherical halo known as the Oort cloud. This distant reservoir of comets may extend tens of thousands of astronomical units away, forming a boundary where the Sun's pole finally yields to the gravity of passing stars. At these distances, the solar system blends into interstellar space. Objects here orbit so slowly that a single revolution can take millions of years. The Sun appears as just another bright star against the galaxy, no longer a dominant presence in the sky. When astronomers speak of the solar system's full extent, they often mean this entire region, from the Sun's blazing core out to the faint edge of its gravitational reach. Now hold that scale in mind. Picture every orbit, every icy body, every distant comet, all enclosed within an enormous invisible bubble of gravity. This is the structure that formed over billions of years through gentle accumulation and chaotic collisions. It feels immense because, from our perspective, it is. Yet this entire system is still small enough to fit inside something far more extreme. The black hole in question possesses an event horizon so vast that if it were placed where our Sun is now, its boundary would extend far beyond the orbit of Pluto, not the accretion disk, not the surrounding chaos, but the event horizon itself, the point of no return. Everything inside that boundary, planets, asteroids, comets, would be swallowed without ever touching the singularity at the center. This comparison is difficult to internalize because an event horizon is not a physical surface. It is not a wall or a shell. It is a geometric boundary in spacetime, defined purely by gravity. Crossing it does not require contact. It simply marks the distance at which escape becomes impossible. That this invisible boundary could encompass the entire known solar system is what makes the scale so unsettling. Step by step, the mind resists this recalibration. We are used to thinking of black holes as compact, dense objects, massive yet small. Stellar mass black holes are only a few kilometers across. Even the supermassive black hole at the center of our galaxy would fit well within Mercury's orbit. This one belongs to a different category entirely, where mass stretches spacetime so broadly that size becomes almost counterintuitive. The sheer enormity comes from gravity itself. As black holes gain mass, their event horizons grow in direct proportion. There is no compression limit forcing them to remain small. Add enough mass, and the horizon expands, calmly and relentlessly, until it spans distances normally reserved for planetary systems. Density at the horizon actually decreases, making these giants strangely gentle at their edges. This is why comparisons matter. Without them, numbers remain abstract. But when the orbit of Pluto becomes a measuring stick, when the outer reaches of our solar system become reference points, the scale takes on meaning. It forces the viewer to abandon familiar intuition and accept that gravity can sculpt space on dimensions that feel almost unreal. By the time this recalibration settles in, the statement no longer feels like exaggeration. It feels like a factual warning. The solar system, vast as it seems from Earth, is not a universal standard of size. In the presence of an ultramassive black hole, it becomes a minor feature, a delicate structure that could disappear entirely inside a single gravitational boundary. We begin where we always do, on the surface of Earth, standing on a planet that feels solid, stable, and permanent beneath our feet. From here, the sky looks familiar. Blue by day, dark by night, scattered with points of light that seem fixed and unchanging. Yet even now, we are already moving. Earth spins beneath us at hundreds of meters per second. It races around the Sun at 30 kilometers per second. And the Sun itself carries us through the galaxy at a speed so great it defies intuition. Motion is the rule, not the exception, even when everything feels still. As we rise gently away from the surface, gravity loosens its grip. Continents curve beneath us, Clouds thin, and the atmosphere fades into black. The moon appears ahead, not as a distant ornament, but as a real place, locked in its slow orbit. We pass it in hours, leaving behind the region where human exploration has ever reached. Earth shrinks into a pale sphere, fragile and finite, suspended in darkness. Beyond the moon's orbit, the familiar sense of scale begins to dissolve. Distances stretch, orbits widen. We cross the paths of satellites, then the realm of space debris, then nothing at all. The sun dominates our view, brilliant and overwhelming, its light filling everything. Mercury flashes by first, a scorched world hugging close to the sun. Venus follows, shrouded in thick clouds, glowing faintly. Earth's orbit passes beneath us, already far behind. Then Mars, smaller and colder, a red point against the void. Past Mars, the space between worlds grows wider. The asteroid belt is not a dense field of tumbling rocks, but a vast, quiet region where individual objects drift millions of kilometers apart. We pass through it without resistance, watching fragments of ancient collisions glide silently by. Ahead, Jupiter looms into view, enormous and complex, its swirling clouds and immense gravity shaping everything nearby. Its moons form miniature systems of their own, each locked in gravitational dance. Saturn follows, its rings spread wide and thin, an illusion of solidity from afar. Then Uranus and Neptune, distant and blue, marking the edge of the planetary domain. Light from the sun is weaker here, diluted across billions of kilometers. The inner solar system feels impossibly far away, reduced to a single bright star behind us. Yet the journey is only beginning. Beyond Neptune lies the Kuiper Belt, a disk of icy remnants left over from planetary formation. Pluto passes quietly below us, one among many similar worlds. Its slow orbit takes centuries, a reminder that time itself stretches as distance increases. Objects here move with deliberate patience, bound loosely by the sun's fading pull. As we continue outward, even the Kuiper Belt thins and fades. The sun's influence weakens, but it does not end abruptly. We enter the realm of the Oort cloud. It's a vast spherical halo of icy bodies extending tens of thousands of times farther from the sun than Earth ever was. Here, orbits are so slow and fragile that passing stars can alter them. A single gravitational nudge can send comets plunging inward or drifting away forever. From this distance, the sun is no longer dominant. It is simply one star among billions, indistinguishable without careful measurement. The solar system, once immense, now feels small, contained within an invisible boundary of gravity. We have not yet left it, but its edges are no longer obvious. Space has become deep, quiet, and profoundly empty. At this point, explanation gives way to experience. There are no landmarks, no structures, only motion through darkness. Distances are measured not in kilometers, but in light years. Time itself feels altered, stretched thin by scale. We are no longer traveling through a neighborhood. We are crossing a threshold. The familiar has fallen away behind us. What remains is the sense of forward movement, of leaving one context entirely and entering another. The solar system, once the full extent of everything we knew, is now just a memory, a compact island of order surrounded by vast emptiness. Ahead lies interstellar space, and beyond that, something far more extreme. This journey is not about speed or technology. It is about perspective. With every passing moment, the structures that once defined our sense of size lose their meaning. The planets, the sun, even the outermost reaches of the solar system fade into insignificance against what comes next. We continue forward, carried by imagination and physics alike, toward a destination that will force us to rethink what size, distance, and gravity truly mean. We are not rushing. There is no urgency. The calm of this passage is intentional. It allows the mind to let go of old scales and prepare for new ones. Because the object we are moving toward does not fit comfortably within the framework of planets and orbits. It exists on a level where entire systems become reference points, where familiar boundaries are erased. As the last traces of the solar system dissolve behind us, the journey becomes something else entirely. We are no longer leaving home. We are approaching a place where the universe itself behaves differently, where gravity dominates space on a scale that defies everyday understanding. And this sense of motion, this quiet departure, is what makes what comes next possible to comprehend at all. As the solar system falls away behind us, the darkness ahead begins to take on structure. Points of light multiply, not randomly, but in patterns that hint at something far larger than any planetary system. What once appeared as a soft, milky band across Earth's night sky now reveals itself as what it truly is. Milky Way, a vast rotating island of stars suspended in space. From within, the Milky Way feels boundless. It contains hundreds of billions of stars, each with its own history, many with planets of their own. Its spiral arms stretch for tens of thousands of light years, wrapped around a dense central core, glowing with ancient starlight. Clouds of gas and dust thread through its disk, birthing new stars even as older ones burn out and fade. Gravity binds it all together into a coherent, rotating structure that has persisted for more than 13 billion years. As we pull farther back, the galaxy's full scale becomes apparent. The Sun, once dominant, is now invisible without magnification, lost among countless similar stars. The Milky Way spans roughly 100,000 light-years from edge to edge. Light itself, the fastest thing in the universe, requires 100 millennia to cross it. From this vantage point, the galaxy feels less like a collection of objects and more like a single entity. A massive system shaped by gravity on a scale difficult to truly grasp. At its center lies something even more extreme. Buried within dense clouds of gas and stars is Sagittarius A*, a black hole containing about 4 million times the mass of our Sun. It is the gravitational anchor of the entire galaxy, the object around which everything ultimately orbits. Stars near the core move at extraordinary speeds, tracing tight paths that betray the presence of an immense, unseen mass. By any reasonable standard, this is a monster. A black hole millions of times more massive than the Sun sounds almost absurd when compared to stellar remnants formed from collapsing stars. Sagittarius A* would easily swallow the entire inner solar system without effort. It warps space-time in its vicinity, influences star formation, and plays a quiet but fundamental role in the galaxy's long-term evolution. And yet, as vast and powerful as the Milky Way feels, it is not unique. It is one of hundreds of billions of galaxies in the observable universe. As we continue to drift outward, neighboring galaxies emerge. Andromeda appears first, our nearest large companion, itself containing perhaps 1 trillion stars and destined to collide with the Milky Way billions of years from now. Around them, smaller satellite galaxies cluster like moths around lanterns. The farther we go, the more the sense of dominance erodes. The Milky Way, once the entire universe from a human perspective, becomes just one structure among many. Galaxies arrange themselves into groups, clusters, and superclusters, linked by vast filaments of dark matter and separated by enormous cosmic voids. Gravity operates here on scales that dwarf even galactic dimensions, shaping the universe into a web of staggering complexity. This is where perspective begins to collapse. The galaxy that once felt impossibly large now fits comfortably within a larger framework. Its 100,000 light-year diameter, once awe-inspiring, becomes a modest unit of measurement. Even its central black hole, with millions of solar masses, starts to feel like a familiar benchmark rather than an extreme outlier. That shift in perception is subtle but profound. It reveals how easily intuition fails when scale increases beyond everyday experience. Each layer of structure makes the previous one feel smaller, less significant, more fragile. The Milky Way still matters, still dominates our local region of space, but it no longer feels like the ultimate expression of gravity's power. And this is precisely why it serves as the perfect reference point. By first allowing the galaxy to feel immense, by emphasizing its size, its mass, its central black hole, the mind establishes a sense of what large means in cosmic terms. Only then can that sense be challenged. Because what lies ahead does not merely exceed planetary scales or stellar scales. It does not simply rival the mass of Sagittarius A*. It dwarfs it. The object we are moving toward belongs to a category so extreme that even supermassive black holes, like the one anchoring our galaxy, begin to look modest by comparison. This realization does not arrive all at once. It settles gradually as the Milky Way recedes into the background, becoming just another spiral among countless others. Its glow fades. Its structure flattens into a thin disk of light. Eventually, even that disk becomes a faint smudge, indistinguishable without careful observation. The humbling effect is unavoidable. Everything we associate with home, with permanence, with scale, is revealed as provisional. Galaxies are not endpoints. They are intermediate structures, steps in a hierarchy shaped by gravity across ever larger distances and longer times. The universe does not stop at the scale we find most impressive. By the time the Milky Way slips fully into insignificance, the mind is primed for escalation. The benchmark has been set and quietly surpassed. The viewer has been led, step by step, to accept that even the largest familiar structures are not limits, only references. Gravity has no obligation to stop where our intuition feels comfortable. Ahead in the deep cosmic past, there exists an object whose mass exceeds that of Sagittarius A* by orders of magnitude. An object so luminous that it outshines entire galaxies. An object whose gravitational influence defines regions of space comparable to the full extent of planetary systems. The Milky Way, vast as it is, will soon serve only as a measuring stick. A reminder of how small even giants can become when the universe decides to push its own boundaries. And it is from this humbled perspective that the next revelation becomes possible. Beyond the galaxies, space changes character. The glow of clustered stars thins until darkness dominates the view. Not the soft darkness of night skies on Earth, but a deep, ancient black that feels absolute. The nearby islands of light fall away one by one, shrinking into faint points before vanishing entirely. We enter intergalactic space, a realm where distances are so large that even galaxies become rare landmarks. Here, emptiness is the defining feature. You could travel for millions of light years in any direction without encountering a single star. There are no suns to warm the darkness, no planets tracing graceful orbits, no nebulae glowing faintly in reflected light. The temperature hovers just above absolute zero, set by the lingering afterglow of the Big Bang itself. Space is not merely empty here. 'Tis quiet, ancient, and profoundly indifferent. As we continue outward, faint structures begin to emerge, not as individual objects, but as patterns. Galaxies appear again, but not scattered randomly. They arrange themselves into long chains and sheets, stretched across enormous distances like threads in a cosmic tapestry. These filaments intersect at dense nodes where clusters of galaxies gather, while vast voids open between them, regions so empty they seem almost unreal. This is the large-scale structure of the universe, shaped by gravity acting over billions. of years, the filaments themselves are enormous beyond ordinary comprehension. Each one can span hundreds of millions of light-years, containing thousands of galaxies bound loosely together by invisible scaffolding of dark matter. Along these structures, matter flows slowly, guided by gravity toward regions of higher density. It is a process so gradual that human lifetimes are meaningless by comparison. Yet relentless over cosmic time, between these filaments lie the voids. They are not small gaps, but colossal expanses, tens or even hundreds of millions of light-years across, containing almost nothing. A few lonely galaxies drift through them, isolated and starved of material, evolving differently from their clustered counterparts. In these voids, the universe feels stripped to its bare minimum, a reminder that most of space is defined by absence rather than presence. The farther we travel, the more the sense of isolation deepens. There is no up or down, no foreground or background, only distance layered upon distance. Light from distant galaxies grows fainter and redder, stretched by the expansion of the universe itself. What reaches us is ancient, emitted when the cosmos was younger, denser, and more violent. Each photon carries history, but that history is increasingly difficult to read as signals weaken and time stretches. This is where intuition begins to fail completely. On Earth, distance is measured in kilometers, sometimes in hours or days of travel. Even within the solar system, scale can still be tied to familiar concepts like time delay or orbital motion. Here, distance becomes abstract. Millions of light years lose their emotional impact, even though each unit represents a span so vast that civilizations could rise and fall countless times within it. Yet there is structure even here, subtle and grand. Gravity, operating patiently since the universe's earliest moments, has carved patterns into this emptiness. Tiny density variations present shortly after the Big Bang grew over time, drawing matter inward along dark matter filaments. We see now as the result of that slow amplification, a universe shaped not by chaos, but by the quiet persistence of physical law. As we move deeper into this realm, the universe itself begins to look different. Galaxies appear younger, more irregular, their shapes less settled. Star formation rates increase. Collisions and mergers become more common. We are not just moving through space, but backward through time, approaching an era when structure was still assembling. The calm, orderly universe nearby gives way to one that feels more restless, more dynamic. Isolation here is not merely physical, but conceptual. There are no familiar reference points left. The Milky Way is long gone, lost among countless other galaxies now equally distant and indistinct. Even galaxy clusters blur together, their individual identities swallowed by scale. What remains is the sense of being suspended in something far larger than any single object or system. This vastness has a psychological weight. It confronts the mind with the reality that most of the universe is not filled with stars or planets or life, but with space itself. The structures we care about, the places where complexity flourishes, occupy only a tiny fraction of the total volume. Everything else exists as connective tissue, the dark canvas upon which the brighter details are painted. Yet it is precisely this emptiness that makes the next revelation possible. In a universe so large, so sparsely populated, the existence of anything extraordinarily bright or massive becomes even more striking. Against this backdrop of darkness, a single intense source of light can dominate entire regions of space. In the void, contrast is absolute. As we continue forward, that contrast begins to emerge. Far ahead, barely distinguishable at first, a point of light stands out. It does not belong to any nearby cluster. It does not fade like distant galaxies do. Instead, it grows slowly brighter as everything else recedes. It is a beacon, piercing the darkness with energy released when the universe was young. The immensity of the surrounding emptiness amplifies its presence. In a crowded region, such a light might blend into background noise. Here, surrounded by near total absence, it commands attention. The void itself seems to frame it, emphasizing its significance by stripping away distractions. This slow approach is deliberate. It allows the mind to adjust to the scale of intergalactic space, to accept the loneliness and vastness as baseline conditions. Only then can the significance of what lies ahead be fully appreciated. The universe has been reduced to its essentials: gravity, space, time, and a single, distant source of overwhelming power. In this deep intergalactic darkness, the viewer is humbled not by complexity, but by simplicity. There is almost nothing here, and yet that nothing stretches farther than imagination comfortably allows. The sense of isolation is complete. Home is impossibly far away. Familiar structures no longer anchor perception. What remains is the realization that the universe is not built around places like ours, but around laws that operate impartially across unimaginable distances. From within this emptiness, the next escalation begins. The darkness does not last forever. Ahead, the lone beacon continues to grow, promising an encounter with something capable of outshining the vast cosmic void itself. At this thing subtle but profound begins to happen to our sense of reality. The farther we travel, the older everything becomes. Distance is no longer just a measure of space. It becomes a measure of time. Light does not arrive instantly. It moves at a finite speed, and that simple fact turns the universe into a kind of natural time machine. When we look at nearby stars, we see them as they were years ago. When we observe distant galaxies, we see them as they were millions or billions of years in the past. The journey outward is also a journey backward, peeling away layers of cosmic history. Each additional light year adds another year to the past we are observing. Each million light years erases another million years of cosmic evolution. This is not metaphorical. It is literal. The photons reaching us now began their journey long before Earth existed. Some set out before the sun ignited. Others left their source when the Milky Way itself was still forming. The universe does not present itself as it is now, but as it was. Frozen into streams of ancient light traveling across expanding space as we continue deeper. We cross a threshold where familiar milestones disappear entirely. There is no Earth, no solar system, no recognizable spiral galaxies. The universe we are seeing is younger, denser, and more chaotic. Structures are still assembling. Matter has not yet settled into the orderly forms we recognize nearby. The idea is initially disorienting. On Earth, time flows forward relentlessly. We remember the past, but cannot revisit it. In the cosmos, the past is everywhere. It surrounds us, layered across the sky, waiting to be observed. By simply looking farther away, we see earlier chapters of cosmic history unfolding in real time. 10 billion light-years away means 10 billion years ago. At that epoch, the universe was barely a quarter of its current age. It was hotter, smaller, and far more violent. Galaxies collided frequently. Star formation rates were dramatically higher. Supermassive black holes were actively feeding, growing, and reshaping their environments. The calm, mature universe we inhabit today did not yet exist. Earth was not even a possibility then. The heavy elements required to build rocky planets, oceans, and life had only begun to accumulate. The sun had not formed. The Milky Way had not settled into its familiar spiral structure. Even the night sky, if there had been observers to see it, would have looked profoundly different. This shift in perspective quietly reorders our sense of importance. Human history spans thousands of years. Civilization reaches back mere millennia. Compared to cosmic time, these intervals vanish into insignificance. Entire species can rise and disappear, while a single galaxy completes only a fraction of a rotation. The universe operates on timescales so vast that human intuition simply does not apply. Yet there is a strange clarity that comes with this realization. The universe is not static. It has a history. It evolves. What we see nearby represents the outcome of processes that began long before anything familiar existed. By observing distant objects, we are not speculating about the past. We are witnessing it directly preserved in light. As we look farther back, galaxies themselves begin to change. Nearby galaxies tend to be well organized, with clear shapes and stable structures. Farther away, those shapes blur. Galaxies appear smaller, clumpier, more irregular. They are still forming, still assembling from smaller pieces. Collisions are common. Starbirth is intense. The universe feels younger because it is younger. This is where intellectual satisfaction begins to emerge. The same laws of physics apply everywhere and everyone. Gravity behaves the same way in the early universe as it does today. Light follows the same rules. Matter responds to the same forces. The difference is not the laws themselves, but the conditions under which they operate. Denser environments produce more dramatic outcomes. Understanding this transforms distance into context. We are no longer just moving toward an object. We are approaching a moment in cosmic history when extremes were more common. The early universe was a place where energy densities were higher, gas was more abundant, and gravitational interactions were more intense. It was a fertile environment for the rapid growth of massive structures. This helps explain why the object ahead exists at all. If such an extreme phenomenon were found nearby in the modern universe, it would be almost impossible to explain. Conditions today are too calm, too depleted of raw material. But in the distant past, the universe had not yet exhausted its resources. It was still rich with gas, still crowded, still violently dynamic. The deeper we look, the more compressed time becomes. Billions of years unfold across the sky simultaneously. Some regions show the universe at one stage of development, others at another. There is no single cosmic now. There are only overlapping snapshots, each representing a different era. This layered view reshapes our sense of causality. The light arriving from distant objects left long before the Milky Way finished forming its spiral arms. It left before the sun ignited. Left before Earth was even a cloud of dust. And yet it arrives here now, intersecting our moment in time as if these vastly different histories were meant to meet. There is something humbling in that convergence. It reminds us that our present moment is not privileged. It is simply one point along an immense timeline. The universe does not aim toward us or revolve around our era. It unfolds according to physical laws, indifferent to whether anyone is watching. As we approach the source of that distant light, we are approaching an era when the universe was young enough to produce extremes. The darkness around us is no longer just empty space. It is filled with history. Every faint glow, every distorted galaxy, every stretched photon carries information from a time when the cosmos was still defining itself. This is why the journey feels different now. We are no longer travelers moving through space alone. We are witnesses moving through time. The object ahead is not just distant, it is ancient. Its light began its journey before our world existed, before our star ignited, before the familiar cosmic order settled into place by the time that light reaches us. It has crossed an evolving universe, expanding, cooling, and changing around it. It carries with it a message from a younger cosmos, one that had not yet learned restraint. Understanding this reframes everything that follows. The extreme nature of what we are about to encounter is not an anomaly of the present universe, but a relic of a more intense past. To comprehend an object that seems impossibly large, impossibly bright, and impossibly early, we must first accept this shift in perspective. We are not just seeing something far away. We are seeing something from a time when the universe itself was still testing the limits of what it could become. At first, nothing more than a point. Against the vast darkness of intergalactic space, it does not look dramatic or imposing. It does not yet announce itself as extraordinary. It is simply brighter than it should be. A single, concentrated source of light where no such thing should dominate. Everything else around it fades into insignificance, not abruptly, but gradually. As if the universe itself is drawing attention toward this one anomaly. As we move closer, the contrast becomes impossible to ignore. Galaxies that once filled our view now appear dim by comparison. Their combined starlight, spread across hundreds of billions of suns, struggles to compete with this lone beacon. It does not flicker like a star or resolve into structure like a galaxy. It remains stubbornly compact, refusing to reveal its true nature all at once. This is where intuition begins to break down. Brightness is supposed to come from size. Entire galaxies shine because they contain unimaginable numbers of stars. To outshine them, an object should be vast, sprawling, complex. And yet this light originates from a region so small that even the most powerful telescopes initially struggled to see it as anything more than a point. The mismatch between power and apparent size creates unease, a quiet signal that something unusual is at work. The longer we observe it, the more unsettling it becomes. Its brightness is not steady in the way galaxies tend to be. It varies over time, subtly but measurably. That variability carries information. It tells us that the region producing the light cannot be enormous, because changes cannot propagate faster than light itself. If the brightness shifts over weeks or months, then the source must be no larger than a few light weeks or months across. The implications of that realization are profound. Imagine compressing the output of an entire galaxy into a region comparable to the scale of our solar system, not spread across spiral arms and star clusters, but concentrated into a single engine. That is the scale the numbers demand. The universe, it seems, has found a way to pack unimaginable energy into an astonishingly small volume. As we draw closer still, the light grows harsher, more intense. It spans a wide range of wavelengths, from radio waves to visible light to powerful X-rays. This is not the gentle glow of stars steadily burning nuclear fuel. It is something far more violent, more efficient, converting mass into energy at a rate that dwarfs anything seen in stellar processes. The surrounding darkness makes the brightness feel almost aggressive. In intergalactic space, there is nothing to soften it, nothing to compete with it. The void becomes a stage, and this point of light commands it completely. It shines across billions of light years, its photons racing outward in all directions, some of them eventually intersecting our own moment in time. Those photons began their journey when the universe was young. They left their source before the sun existed, before Earth formed, before life had any chance to emerge. For billions of years, they traveled through an expanding cosmos, stretched and reddened by the growth of space itself, slipping between galaxies, crossing voids, carrying information from an era long gone. This alone would make the object remarkable, but its brightness pushes it into a different category entirely. To be visible across such distances, even after the universe has expanded and diluted its light, it must be releasing energy at a truly staggering rate. Calculations quickly show that this rate exceeds the combined output of hundreds of billions of stars. The mind resists this conclusion at first. It feels excessive, almost absurd, and yet the data insists. Astronomers encountered this problem decades ago when they first discovered similar objects. Initially, they assumed they were seeing nearby stars with unusual properties. That explanation failed as soon as their distances were measured. The light was shifted toward redder wavelengths, far more than could be explained by motion within our galaxy. The only viable interpretation was that these objects were extraordinarily far away, receding with the expansion of the universe itself. Distance multiplied the mystery. If they were that far, then their brightness had to be intrinsic. There was no trick of proximity, no illusion caused by closeness. The universe was not magnifying a small lamp nearby. It was revealing a cosmic lighthouse blazing across time and space. As our journey continues, the point begins to dominate our view. It does not yet reveal its structure, but its presence is undeniable. Everything else seems secondary now, background noise against its intensity. The void feels less empty, filled instead with the anticipation of what could produce such light. This is where suspense deepens. We know, in broad terms, what kinds of objects exist in the universe. Stars, galaxies, nebulae, clusters. None of them fit this behavior. Each familiar category falls short when tested against the observations. The object refuses to be classified, easily sitting uncomfortably between known types. Demanding a new explanation, there is a reason the name has not yet been spoken. Naming gives comfort. It places something within a conceptual box, a framework that feels manageable. For now, the experience is meant to remain unresolved. A single point of light, too bright, too distant, too concentrated, shining from a time when the universe itself was still finding its shape. The closer we get, the more we sense that this is not just an object, but a process. A continuous release of energy driven by extreme conditions, sustained over millions of years. Whatever fuels it does so relentlessly, without pause. Pouring radiation into the surrounding space and reshaping its environment. This is not a transient flash like a supernova. It does not fade after weeks or months. It persists, stable on timescales that dwarf human history. That persistence adds another layer of mystery. To shine this brightly for this long requires not just an enormous initial event, but a sustained mechanism capable of feeding energy into space year after year, century after century, millennium after millennium. As the light fills more of our view, imagination begins to take over. One cannot help but picture what such a source would look like up close, the colors it might emit, the distortions it might create in the surrounding space, the violence implied by its power. Even before we understand it, even before we name it, the object asserts itself as something beyond the ordinary. This is the power of delayed revelation. By withholding the label, the mind is forced to grapple with the raw facts. Brightness without context, distance without scale, energy without explanation. Each unanswered question tightens the narrative, drawing attention forward rather than allowing it to settle. The universe, in this moment, feels like it is presenting a riddle. Here is a light that should not be able to exist, shining where nothing else does. Here is evidence of a process capable of outshining galaxies while occupying a space no larger than a planetary system. Here is a signal from the distant past, preserved across billions of years, arriving now to challenge our understanding. As we approach the source of that light, the suspense does not resolve. it intensifies. The object grows larger, brighter, more defined, yet still resists simple explanation. We are close enough now to know that whatever this is, it represents one of the most extreme phenomena the universe has ever produced. Only, now, with the scale of its brightness firmly established, with the mystery fully formed, does it make sense to ask the final question? What kind of object can burn so brightly for so long across such distances? What engine could possibly power a beacon capable of announcing its presence across the observable universe? The answer exists, but it will not feel any less astonishing than the question itself. The point of receives a name. Astronomers call it TON 618, a designation that sounds almost modest given what it represents. Hidden behind that simple label is one of the most extreme objects ever identified in the observable universe. A system so large and powerful that it forces a rethinking of how far gravity can be pushed before it. Breaks expectation. At the heart of TON 618 lies a black hole whose mass defies comfortable intuition. Estimates place it at roughly 66 billion times the mass of our Sun. Not millions, not billions. Tens of billions. To put that into perspective, the supermassive black hole anchoring the Milky Way weighs in at about 4 million solar masses. TON 618 outweighs it by a factor of more than 10,000. This single object contains more mass than many entire galaxies. Mass alone, however, does not fully convey the scale of what this means. Black holes are defined not just by how much mass they contain, but by how that mass shapes spacetime around them. For TON 618, the boundary known as the event horizon would extend roughly 40 times farther than Pluto's orbit if placed at the center of our solar system. Everything we think of as planetary space would lie deep inside a region from which nothing, not even light, could escape. Yet TON 618 is not invisible. Quite the opposite. It shines with the luminosity of roughly 140 trillion suns. This staggering output does not come from the black hole itself, but from the maelstrom of matter spiraling into it. Gas falling inward forms a vast accretion disk, heating to extreme temperatures as friction and magnetic forces tear it apart. Before the material vanishes beyond the event horizon, it radiates energy with extraordinary efficiency, converting mass into light at rates no star could ever achieve. The result is a quasar so bright that it outshines entire galaxies. From billions of light years away, TON 618 appears as a dominant beacon, its light easily detectable despite the immense distance and the expansion of the universe, stretching its photons thinner and redder with every passing epoch. When that light began its journey, Earth did not exist. The Sun had not yet formed. The universe itself was still young, barely a quarter of its current age. This combination of extreme mass and extreme luminosity places TON 618 into a rare category, known as ultramassive black holes. These objects sit beyond the already impressive class of supermassive black holes found at the centers of most large galaxies. Ultramassive black holes represent the far upper edge of what astronomers believe. Gravity can assemble within the available time since the Big Bang. What makes TON 618 particularly remarkable is not just that it exists, but when it exists. Observations place it at a redshift corresponding to a time when the universe was roughly 3 billion years old. That means this black hole reached its enormous mass astonishingly quickly by cosmic standards. The universe simply did not have much time to build something so large, especially given the known limits on how fast black holes are supposed to grow. This is where authority and caution come into play. Astronomers do not assign masses like this lightly. multiple independent methods converge on the same conclusion. Spectral measurements reveal gas moving at incredible speeds, indicating a deep gravitational well. Luminosity measurements set a lower bound on mass based on the maximum brightness a black hole of a given size can sustain before radiation pressure blows incoming material away. Together, these constraints consistently point to a black hole in the tens of billions of solar masses. Even allowing for uncertainty, the conclusion remains unavoidable. TON 618 is not merely large. It is among the largest black holes ever discovered. Some estimates allow its true mass to be somewhat lower or higher, but even at the low end, it remains an object of almost unimaginable scale. There is no plausible interpretation in which it becomes ordinary. This realization anchors its identity firmly. TON 618 is not just another quasar. It is a benchmark. It's a reference point against which all other known black holes can be compared. When astronomers talk about extremes, this object sits near the top of the list. A natural stress test for theories of black hole growth and cosmic evolution. The shock does not come from a single number, but from how those numbers interact. Mass on this scale implies a gravitational influence extending across distances normally associated with planetary systems. Luminosity on this scale implies a sustained conversion of matter into energy at rates unmatched anywhere else in the universe. Age on this scale implies that all of this happened rapidly, under conditions that must have been exceptionally favorable. What emerges is a portrait of a system operating at the absolute limits of what physics allows without breaking. It does not violate known laws, but it pushes them to their extremes. Gravity, magnetism, relativity, and thermodynamics all play roles in sustaining this object. Yet none alone can fully explain how it reached its current state so efficiently. There is also a subtle psychological shift that occurs once the name and nature of the object are known. The mysterious point of light becomes something concrete. It acquires an identity within the cosmic hierarchy. It is no longer an anomaly without context, but a specific example of the most powerful engines nature has devised. This anchoring allows the mind to hold on to it as a real thing, not just an abstract concept. And yet, knowing its name does not make it feel less alien. If anything, it sharpens the sense of unease. TON 618 represents a reminder that the universe is capable of assembling structures far beyond the scales we encounter locally. It shows that under the right conditions, gravity can dominate space itself, creating objects whose influence is measured not in kilometers or even light years, but in entire planetary systems. It also reframes our understanding of rarity. Objects like this are uncommon, but the universe is vast enough that even rare processes can occur multiple times. TON 618 is exceptional, but it is not necessarily unique. Its existence implies that there may be other ultramassive black holes scattered across the distant cosmos, waiting to be discovered in similar epochs. By revealing TON 618 for what it is, the narrative reaches a crucial pivot point. The mystery of brightness has been answered, but a deeper mystery replaces it. How does something like this form? How does it grow so massive so quickly? And what does its existence tell us about the universe during its most violent and productive years? These questions linger deliberately. The reveal is not an ending, but a foundation. TON 618 now stands as a known quantity, an extreme yet measurable object anchored in data and observation. From here, the story shifts from what it is to how it came to be, and what encountering something of this magnitude means for our understanding of reality itself. The universe has revealed one of its largest creations, not as a fleeting spectacle, but as a persistent presence shining steadily across billions of years. With its identity established, the challenge is no longer disbelief, but comprehension. Belief, but comprehension. To understand like this shines so intensely, it helps to set aside the idea that black holes themselves emit light. They do not. By definition, anything that crosses the event horizon is lost to the outside universe. No photons escape, and yet some of the brightest objects ever observed are powered by black holes. The paradox resolves itself when we focus not on what disappears inside, but on what happens just before it does. Surrounding an actively feeding black hole is a structure known as an accretion disk. It forms because matter rarely falls straight inward. Gas clouds drifting through a galaxy carry angular momentum, a kind of cosmic inertia that causes them to orbit rather than plunge directly toward the center. As this material is drawn inward by gravity, it spreads into a flattened, rotating disk, spiraling ever closer to the black hole dot at large distances from the center. This disk can appear almost gentle. Gas moves relatively slowly. Temperatures remain modest by cosmic standards, and radiation output is limited. But the closer material gets to the black hole, the more extreme the conditions become. Orbital speeds increase dramatically. Gas that once drifted at hundreds of kilometers per second begins to race around at thousands, then tens of thousands, eventually reaching significant fractions of the speed of light. This acceleration is not smooth. Different parts of the disk orbit at different speeds. Inner regions move faster than outer ones, creating shear. Layers of gas rub against each other, collide, and churn. That friction converts orbital energy into heat. Temperatures climb rapidly, reaching millions and then billions of degrees. Matter is no longer a gas in the familiar sense. It becomes plasma, a seething mixture of charged particles stripped of their electrons. At these temperatures, thermal radiation alone would be impressive, but it is only part of the story. The plasma within the accretion disk carries electric charge, and moving charges generate magnetic fields. As the disk rotates, those magnetic fields are twisted, stretched, and amplified. They thread through the disk like invisible ropes, linking regions moving at different speeds. These magnetic fields play a crucial role in solving a fundamental problem. For matter to fall inward, it must lose angular momentum. Without a way to shed that momentum, material would simply orbit forever, trapped in stable paths around the black hole. Magnetic interactions provide the escape route. They transfer angular momentum outward, allowing inner material to spiral closer while outer material is pushed farther away. This process is not orderly. It is turbulent, violent, and chaotic. Magnetic field lines snap and reconnect, releasing sudden bursts of energy. These reconnection events produce flares, accelerating particles to extreme energies and generating radiation across the electromagnetic spectrum. The accretion disk becomes a dynamic environment, constantly reshaping itself under the combined influence of gravity, pressure, and electromagnetism. As matter spirals inward, it falls deeper into the black hole's gravitational well. Gravitational potential energy is converted first into kinetic energy as material speeds up, then into thermal energy through friction and magnetic turbulence. By the time the gas reaches the innermost regions of the disk, it has lost an enormous amount of energy. That energy does not vanish. It is radiated outward in the form of light. This is where black hole accretion becomes astonishingly efficient. In everyday chemical reactions, only a tiny fraction of mass is converted into energy. Even nuclear fusion, the process powering stars, converts less than 1% of mass into energy. Accretion onto a black hole can convert 10%, 20%, or even more depending on how fast the black hole is spinning. In some cases, nearly half of the infalling matter's mass energy can be released before it disappears beyond the event. Horizon. The reason lies in relativity. Near a black hole, gravity warps space and time so severely that stable orbits exist only down to a certain radius. This boundary is known as the innermost stable circular orbit. Inside it, no orbit is possible. Matter plunges inward inevitably. As gas approaches this boundary, it reaches its highest speeds and temperatures, radiating energy at maximum efficiency. A relatively small amount of matter can produce an extraordinary amount of light. Spin adds another layer of complexity. Many supermassive black holes rotate rapidly, dragging space-time around with them in a phenomenon known as frame dragging. This rotation allows material to orbit closer to the event horizon before becoming unstable. The closer the orbit, the more gravitational energy can be extracted. A rapidly spinning black hole effectively opens a deeper energy reservoir, allowing accretion disks to shine even more brightly. In some cases, magnetic fields tap directly into the black hole's rotation through processes that remain inactive. Area of research energy can be extracted from the black hole's spin itself and channeled into powerful jets and radiation. These jets can launch particles at near light speed, blasting energy far beyond the accretion disk and influencing regions thousands or even millions of light-years away. The combined result of all these mechanisms is staggering luminosity. The accretion disk does not glow gently. It blazes. Different regions emit different wavelengths. Outer regions radiate infrared and visible light. Inner regions produce ultraviolet and X-rays. It's the hottest, most extreme zones near the black hole emit high-energy radiation that can ionize atoms and strip electrons from even the heaviest elements. This radiation is not merely a byproduct. It actively shapes the environment. Intense light exerts pressure. Photons carry momentum, and when they strike matter, they push it outward. At sufficiently high luminosities, radiation pressure can counteract gravity itself, limiting how quickly material can fall inward. This balance defines a fundamental ceiling on accretion known as the Eddington limit. Push harder, and the disk begins to blow itself apart. Yet some systems approach this limit and linger there for millions of years. They hover at the edge of stability, converting matter into energy at astonishing rates without fully shutting down. This delicate balance is what allows quasars to shine so brilliantly for so long. They are not brief explosions. They are sustained engines, powered by a steady flow of matter spiraling toward oblivion. Relativistic effects further shape what we observe. At speeds approaching that of light, time dilates, lengths contract, and radiation is beamed in the direction of motion. Portions of the disk rotating toward us appear brighter than those rotating away, an effect known as relativistic beaming. Gravity itself bends light, allowing us to see parts of the disk that would otherwise be hidden behind the black hole. The result is a distorted, asymmetric glow that encodes information about the black hole's mass and spin. Understanding all of this requires more than intuition. It demands detailed calculations grounded in general relativity and plasma physics. Modern simulations track billions of interacting particles, magnetic fields, and curved spacetime, pushing the limits of supercomputing. These models are not perfect, but they reproduce many of the features astronomers observe. From spectral signatures to variability patterns, what builds trust in this explanation is its consistency. The same physical principles explain the behavior of smaller black holes, larger ones, and systems across cosmic history. Scale changes the numbers, but not the rules. Gravity accelerates matter. Friction and magnetic fields heat it. Relativity governs the final approach. energy is released. Before disappearance, cause leads to effect, step by step, without invoking exotic, unknown forces. When all of these processes are operating simultaneously, the result is an object capable of outshining galaxies while occupying a region no larger than a planetary system. The brightness is not magic. It is the logical consequence of mass, motion, and energy interacting under extreme gravity. This is why black holes, despite their reputation as cosmic destroyers, are also among the most luminous phenomena in the universe. They do not shine because they defy physics, but because they obey it so completely. They exploit gravity's rules to their fullest extent, converting and falling matter into radiant energy with ruthless efficiency. In the case of the most extreme systems, this process reaches an almost surreal level. Vast quantities of gas are funneled into a compact region. Speeds climb toward light itself. Space-time bends. Magnetic fields twist and snap. Energy pours outward in torrents. And all of it happens just outside a boundary beyond which nothing can ever return by understanding the mechanics of accretion. The brightness ceases to feel mysterious, but it does not become mundane. If anything, comprehension deepens the awe. The universe has found a way to build engines that rival its largest structures in power while remaining astonishingly compact. Black holes shine brightly, not in spite of their darkness, but because of it, because the path to nothingness is paved with extraordinary releases of energy. To grasp extreme black hole power truly is, it helps to step back and compare it with the energy processes we already understand. In everyday life, energy feels expensive. Vast amounts of fuel are burned to produce relatively modest results, even on planetary scales. The sun feels like the ultimate benchmark, a star converting matter into light steadily for billions of years. Yet black holes operate on an entirely different level, one that forces a fundamental reframing of what energy really is. At the root of this comparison lies a single equation, one of the most famous in all of science, Albert Einstein's E equals mc squared. It looks deceptively simple. Energy equals mass multiplied by the speed of light squared. But hidden inside that equation is an almost incomprehensible amplification factor. The speed of light is enormous, about 300 million meters per second squared. It becomes a number so large that even a tiny amount of mass corresponds to a staggering quantity of energy. This equivalence between mass and energy is not theoretical speculation. It has been confirmed repeatedly, from nuclear reactions to particle physics experiments. What varies across different processes is not whether mass can become energy, but how efficiently that conversion happens. And it is efficiency that separates black holes from everything else we know. Start with chemical reactions, the kind that power engines, fires, and biological metabolism. When gasoline burns or food is metabolized, energy is released through the rearrangement of electrons around atomic nuclei. The mass involved does change, but by such a tiny amount that it is practically undetectable. Roughly 1/1000th of the original mass becomes energy. Chemical energy feels powerful to us because human scales are small. But in cosmic terms, it is almost negligible. Nuclear reactions take a dramatic step up. In nuclear fission, heavy atoms split into lighter ones, releasing energy because the combined mass of the fragments is slightly less than the original nucleus. In nuclear fusion, light atoms merge into heavier ones, again releasing energy through a small mass difference. Fusion is what powers stars. In the core of the Sun, hydrogen nuclei fuse into helium, converting about 0.7% of the original mass into energy. That 0.7% may sound small, but multiplied by the Sun's enormous mass, it is enough to keep it shining for billions of years. Every second, the sun converts roughly 4 million tons of mass into energy. This output defines our intuition for stellar power. It feels immense because it is. Entire planetary systems depend on it. Black hole accretion, however, does not play by the same rules. It is not limited by nuclear binding energies or electron configurations. Instead, it taps directly into gravity itself. When matter falls toward a black hole, it releases energy, not because its nuclei change, but because it descends into an extraordinarily deep gravitational well. That descent strips away energy far more efficiently than fusion ever could, depending on the black hole's spin. Between 10 and 40% of the infalling matter's rest mass can be converted into energy before crossing the event horizon. In some theoretical scenarios, the efficiency can be even higher when rotational energy is extracted. This means that black hole accretion can be dozens of times more efficient than nuclear fusion, and millions of times more efficient than chemical reactions. The scale shock here is profound. Take 1 kilogram of matter. If you burn it chemically, you release energy equivalent to a small explosion. If you fuse it in a star, you release energy comparable to a powerful nuclear device. If you could feed that same kilogram into an idealized black hole accretion disk, the energy released could rival that of a large thermonuclear bomb, all without violating a single law of physics. This reframes black holes entirely. They are not merely sinks that swallow matter and erase it from the universe. They are among the most efficient energy converters that exist. They turn mass into radiation with ruthless effectiveness, squeezing nearly everything that can be extracted, before allowing matter to vanish forever. What makes this even more astonishing is that the process does not require rare or exotic fuel. It works with ordinary matter: hydrogen, helium, dust, gas, even stars. Anything with mass can be fed into the accretion disk. Gravity does not care about composition. It only cares about mass and motion. The reason gravity can achieve this efficiency lies in the depth of the gravitational potential near a black hole. As matter falls inward, it loses potential energy continuously. That energy has to go somewhere. In most gravitational systems, like planets orbiting stars, only a small fraction of potential energy is released as heat. The rest remains locked. In orbital motion, near a black hole, there is no such luxury. Orbits end. Stability disappears. Almost all available energy must be shed. Relativity sharpens this effect. Near the event horizon, time slows, space warps, and energy extraction becomes extraordinarily effective. Matter can orbit multiple times, radiating energy with each pass before finally plunging inward. The closer it gets, the more energy it releases per unit mass. The black hole acts like a cosmic vice, squeezing energy out of matter until almost nothing is left. This is why quasars shine so brightly. It is not because they contain more fuel than galaxies, but because they use their fuel so efficiently. A quasar can outshine a galaxy while consuming far less total mass, simply because it converts that mass into energy at a much higher rate. The cognitive astonishment comes when these efficiencies are scaled up to the mass flows involved in systems like Ton 618. Each year, tens of solar masses worth of material spiral into the accretion disk. With even 10% efficiency, the energy released is equivalent to converting multiple suns entirely into pure radiation every year. And this process can continue for millions of years. At this point, intuition fails completely. There is no everyday experience to anchor these numbers. Even stellar processes feel tame by comparison. The sun's steady glow becomes a gentle candle next to a quasar's furnace. Entire galaxies, luminous as they are, struggle to compete with a single compact region surrounding a black hole. Einstein's equation becomes more than a formula. It becomes a lens through which the universe reveals its extremes. Mass is not just substance. It is stored energy waiting for the right conditions to be released. Black holes provide those conditions more effectively than anything else known. There is also a deeper philosophical shift embedded here. Energy is often thought of as something abstract, something that flows or moves. Black hole physics reminds us that energy and mass are the same thing, viewed from different perspectives. What looks like matter in one context becomes radiation in another. The universe does not distinguish sharply between the two. This realization changes how we think about cosmic power. The brightest objects are not necessarily the largest. They are the most efficient. They are the ones that exploit fundamental relationships to their limits. Black holes do not need to burn fuel in the traditional sense. They let gravity do the work. Authority enters not through appeal, but through consistency. The same equation that explains why the sun shines also explains why quasars blaze. The difference lies not in the theory, but in the environment. Change the gravitational conditions, and the same laws yield radically different outcomes. By the time this comparison settles in, the brightness of ton 618 no longer feels mysterious. It feels inevitable. Given a black hole of that mass, given sufficient fuel, and given the efficiencies allowed by relativity, the energy output follows naturally. The shock comes not from the math, but from accepting that nature allows such extremes at all. This reframing is essential. Without it, the numbers feel arbitrary, even exaggerated. With it, they become unavoidable consequences of physical law. The universe is not being dramatic. It is being consistent, applying the same rules everywhere, even when the results overwhelm human intuition. In the end, black hole efficiency forces a humbling conclusion. The most powerful engines in the cosmos are not stars or explosions, but quiet, persistent processes driven by gravity. They do not announce themselves with sudden flashes. They shine steadily, relentlessly, converting matter into light with an effectiveness that makes all other energy sources look almost wasteful by comparison. Understanding this does not make the phenomenon less astonishing. It deepens the astonishment. It reveals that the universe, through simple equations and fundamental constants, has access to power levels that dwarf anything we can imagine building. And it uses that power not sparingly, but openly, broadcasting it across billions of light years for anyone capable of seeing to witness. Anyone capable of seeing to witness. Once the whole power are understood, a deeper and more unsettling question emerges. Brightness explains how ton 618 shines. Accretion explains where the energy comes from. But neither answers the most difficult problem of all. How did something like this grow so large so early in the history of the universe? This is known among astronomers as the growth problem, and ton 618 sits at its extreme edge. The issue is not whether black holes can become massive. We see supermassive black holes at the centers of many galaxies, including our own. The issue is time. The universe has only existed for a finite span, and the laws governing accretion impose strict limits on how quickly mass can be added. The most important of these limits is the Eddington limit. It arises from a simple balance of forces. As matter falls toward a black hole and heats up, it radiates light. That light carries momentum. When photons collide within falling gas, they push outward. At low luminosities, gravity easily overcomes. This pressure and accretion proceeds. But as luminosity increases, radiation pressure grows stronger. Eventually, it becomes powerful enough to counteract gravity and halt further infall. The Eddington limit defines the maximum steady brightness a black hole of a given mass can sustain while continuing to accrete. Shine brighter than that, and the system begins to blow its own fuel away. Importantly, this is not a limit on how massive a black hole can be, but on how fast it can grow. It acts as a kind of cosmic speed limit. Under ideal conditions, a black hole accreting continuously at the Eddington limit grows exponentially, doubling its mass roughly every 50 million years. That sounds fast, but cosmic scales quickly erode the advantage. Starting from a small seed, many doublings are required to reach tens of billions of solar masses. This is where the timeline becomes uncomfortable. Observations show ton 618 as it existed when the universe was only about 3 billion years old. That leaves, at most, a few billion years for growth from whatever initial seed formed after the first stars. Even under optimistic assumptions, that is just barely enough time, and only if accretion proceeds almost continuously at near maximum rates. Real systems, however, are rarely ideal. Fuel supplies fluctuate. Galaxies undergo periods of calm and chaos. Gas can be blown away by radiation, consumed by star formation, or locked into stable orbits that resist inward flow. Accretion is expected to be intermittent, not smooth. Long stretches of quiet are punctuated by brief feeding episodes. Every pause slows growth. The math becomes even more challenging when starting conditions are considered. The earliest black holes likely formed from the collapse of massive stars, producing seeds with masses on the order of tens or hundreds of suns. Growing from such a seed to 66 billion solar masses requires an almost uninterrupted chain of favorable circumstances. Any significant delay, any extended starvation, and the numbers stop working. Fuel presents another constraint. To build a black hole of this mass, an enormous amount of matter must pass through the accretion disk, even accounting for the fact that not all infalling mass becomes part of the black hole. The total amount of gas required is staggering. It rivals the entire baryonic mass of a large galaxy. That gas must not only exist, but be delivered efficiently to the center over long periods. This raises uncomfortable questions about galactic environments in the early universe. Gas tends to settle into rotating disks. Angular momentum resists. Collapse, getting material to spiral inward, requires mechanisms to strip that momentum away. Galaxy mergers can help by violently disturbing orbits, but mergers are chaotic and disruptive. They do not guarantee smooth, sustained feeding. There is also the issue of self-regulation. As black holes grow brighter, their radiation heats surrounding gas, making it harder for that gas to cool and fall inward. Powerful winds can expel material entirely, shutting down accretion. This feedback process is thought to be responsible for limiting the growth of most supermassive black holes and shaping the evolution of their host galaxies. Ton 618 appears to have grown despite all of these obstacles. That fact alone suggests that at least one of our assumptions is incomplete. Either the initial seeds were much larger than traditionally assumed, or accretion can exceed the Eddington limit for extended periods, or the early universe provided unusually efficient delivery mechanisms, or all of these factors worked together in rare but powerful combinations. Each possibility opens new questions rather than closing old ones. If initial seeds were much larger, how did they form without fragmenting into stars? If accretion exceeded the Eddington limit, how did radiation fail to halt the inflow? If mergers played a dominant role, how did black holes merge efficiently, without stalling for millions of years in complex orbital dances? What makes the problem particularly compelling is that TON 618 is not entirely unique. Astronomers have identified other quasars with black holes billions of solar masses when the universe was similarly young. TON 618 simply represents the extreme end of a broader population. Any explanation must account not just for a single outlier, but for a pattern. This creates scientific tension. The standard framework of black hole growth works well in the nearby universe, where timescales are long and environments calmer. It struggles in the early universe, where everything happened faster and under more extreme conditions. The same. Equations that predict steady growth also predict bottlenecks that appear to have been bypassed. One proposed solution involves periods of super-Eddington accretion, where geometry alters the balance of forces. If infalling material forms a thick, enveloping structure rather than a thin disk, radiation may become trapped and carried inward instead of pushing outward. In such cases, accretion rates could temporarily exceed the Eddington limit without shutting down. These episodes would not last forever, but even brief bursts could significantly accelerate growth. Another possibility is that the seeds, they themselves, were unusually massive. In the early universe, before heavy elements existed too. Aid cooling, enormous clouds of hydrogen and helium may have collapsed directly into black holes without forming stars first. Such direct collapse black holes could start life with tens of thousands or even hundreds of thousands of solar masses. Providing a dramatic head start, mergers likely played a role as well. The early universe was crowded. Galaxies were closer together, and collisions were common. When galaxies merged, their central black holes would eventually sink toward the center and combine, producing rapid jumps in mass. Repeated mergers could build up mass far more quickly than accretion alone. None of these ideas is fully settled. Each has supporting evidence and unresolved challenges. Observations are limited by distance and resolution. Simulations push the limits of computing power. The growth problem remains open not because of a lack of effort, but because nature appears to be operating at the edge of what our theories comfortably allow. This is where curiosity is renewed rather than satisfied. TON 618 does not neatly fit into a closed narrative. It acts as a stress test, highlighting where models succeed and where they strain. It invites refinement, not rejection. The laws of physics still apply, but their consequences in extreme environments may be more flexible than once assumed. The existence of TON 618 forces us to confront the possibility that the early universe was exceptionally efficient at building giants. It suggests that under the right conditions, gravity, gas, and time can conspire to produce outcomes that feel almost excessive. The question is not whether this happened, but how often and under what precise circumstances. As long as these questions remain unanswered, the story cannot fully settle. Each proposed solution opens new lines of inquiry. Each observation adds constraints, but also reveals new anomalies. The growth problem remains a living puzzle, one that continues to evolve as new data arrives. In that sense, TON 618 is not just an object to be explained. It is a guidepost pointing toward gaps in our understanding. It reminds us that even well-tested theories can be incomplete at the extremes. And it ensures that the narrative does not end with explanation, but with tension, curiosity, and the promise of deeper insights still to come. Confronted with an extremist TON 618, astronomers are careful not to claim certainty where none exists. Instead of a single explanation, what emerges is a landscape of possibilities, each grounded in known physics, each supported by some evidence, and each carrying unresolved questions of its own. This is not a weakness of science, but a reflection of how knowledge advances at the frontier, where observations arrive before full understanding. One leading idea begins at the very beginning, with the birth of the first black holes themselves. In the simplest picture, black holes form when massive stars exhaust their fuel and collapse, leaving behind remnants tens or perhaps hundreds of times the mass of the Sun. These stellar mass seeds are common and well understood. The challenge is that starting from such small beginnings makes the growth problem especially severe. Even under ideal conditions, too many doublings are required, and too little time is available. This has led to the proposal that some black holes may have been born already large. In the early universe, conditions were very different from those today. Heavy elements had not yet formed in significant quantities, meaning gas cooled less efficiently. Without efficient cooling, enormous clouds of hydrogen and helium could resist fragmenting into stars. Instead of breaking apart, some of these clouds may have collapsed directly under their own gravity, forming black holes with masses of tens of thousands or even hundreds of thousands of suns in a single event. These so-called massive seed or direct collapse black holes provide a dramatic head start. Starting from a seed 1,000 times larger shortens the required growth time substantially. The physics involved does not require new forces or exotic matter, only specific environmental conditions. Intense radiation from nearby star-forming regions could suppress cooling. Rapid inflows of gas could overwhelm stabilizing pressures. The challenge is determining how common such conditions were. Current models suggest they may have been rare, but the universe is vast, and even rare pathways can produce notable outcomes. Another line of explanation focuses not on how black holes start, but on how they feed. The Eddington limit describes a balance between gravity pulling matter inward and radiation pushing it outward. It assumes a relatively orderly accretion disk, thin and radiating efficiently. But nature does not always adhere to tidy assumptions. Under certain circumstances, accretion flows may become thick, turbulent, and enveloping, forming structures where radiation is trapped rather than immediately escaping. In these super-Eddington scenarios, photons generated deep within the accretion flow are carried inward along with the gas, reducing the outward pressure that would otherwise halt accretion. From the outside, the system may still appear near or below the Eddington limit, even while mass is piling onto the black hole at much higher rates. These phases would not be stable forever. But even relatively short episodes could accelerate growth dramatically. Evidence for such behavior exists in smaller systems. Some stellar mass black holes and neutron stars show signs of accreting above classical limits, at least temporarily. Scaling these processes up to supermassive black holes remains challenging. But simulations increasingly suggest that geometry and turbulence can significantly alter how radiation and matter interact. The possibility that early black holes experienced repeated bursts of super-Eddington growth remains an active area of research. Mergers offer a third pathway. The early universe was crowded. Galaxies were closer together, and collisions were far more common than they are today. When galaxies merge, their central black holes do not immediately combine. But over time, they lose energy through interactions with stars and gas, spiraling toward each other until they eventually merge. Such events produce sudden jumps in mass, bypassing the slow grind of accretion. In dense environments, repeated mergers could build up black hole mass rapidly. A black hole that begins modestly could, through a series of galactic collisions, assemble a much larger mass in relatively short cosmic time. Gravitational wave emission during these mergers carries away energy, allowing the final coalescence to proceed. While direct observations of such mergers at extreme distances are still beyond current capabilities, Future detectors are expected to open this window, yet mergers alone are unlikely to be sufficient. They require a population of already massive black holes to collide, which itself demands prior growth. Mergers work best in combination with other mechanisms, amplifying mass gained through accretion rather than replacing it entirely. Fuel availability is another crucial piece of the puzzle. The early universe was far richer in gas than the modern one. Star formation had only recently begun. So much of the baryonic matter was still in diffuse form rather than locked into stars. Galaxies were smaller, less settled, and more prone to funneling gas toward their centers through gravitational instabilities. Bars, spiral arms, and tidal interactions all worked more efficiently to strip angular momentum and drive inflows. In such gas-rich environments, black holes may have had access to near-continuous fuel supplies. Instead of intermittent feeding punctuated by long droughts, some systems may have experienced extended periods of abundant inflow. If Ton 618 resided at the center of a particularly favorable region, such as a forming galaxy cluster or protocluster, it could have drawn material from multiple sources over billions of years. This picture emphasizes environment rather than uniqueness. TON 618 may not have been special because of exotic physics, but because of where it lived. Location matters. A black hole embedded in a nexus of merging gas-rich galaxies would have opportunities unavailable to more isolated systems. The universe, in this view, occasionally creates perfect storms where all growth-enhancing factors align. What makes this field intellectually honest is the willingness to admit uncertainty. None of these explanations has been definitively proven. Each relies on models that push the limits of observation and simulation. Direct collapse seeds are difficult to observe. Super-Eddington accretion challenges classical assumptions. Merger histories are hard to reconstruct across billions of years. Gas inflows depend sensitively on poorly constrained early galactic dynamics, rather than converging on a single answer. Current research suggests that the truth may involve all of these mechanisms operating together. Massive seeds could provide an early boost. Super-Eddington episodes could accelerate growth during key periods. Mergers could add mass in leaps rather than increments. Gas-rich environments could sustain feeding long enough for these processes. To compound, this layered explanation preserves the mystery without surrendering rigor. It acknowledges that the universe is complex and that multiple pathways can lead to similar outcomes. TON 618 may not represent a violation of known physics, but an extreme expression of it, achieved through rare combinations rather than singular miracles. There is also an important psychological dimension to this uncertainty. It resists closure. It prevents the narrative from becoming neat and final. Instead of offering a single, satisfying explanation, it leaves open loops that invite further exploration. That tension is not accidental. It reflects the genuine state of the science. New observations continue to refine these ideas. Infrared telescopes probe the host galaxies of distant quasars, searching for clues about their environments. Radio and millimeter arrays map cold gas reservoirs. X-ray observatories examine the innermost regions of accretion disks. Future gravitational wave detectors promise direct measurements of black hole mergers across cosmic history. Each advance adds constraints, ruling out some possibilities while sharpening others. What remains constant is humility. Astronomers do not claim to have solved the growth problem. They recognize that objects like Ton 618 sit at the edge of current understanding, where confidence must be balanced with openness. The models work well in many regimes, but the extremes still test them. This humility is not resignation. It is motivation. Extreme objects are valuable precisely because they force theory to evolve. They highlight assumptions that went unnoticed. They expose simplifications that no longer hold. In doing so, they drive progress. Ton 618 stands as a reminder that the universe does not always choose the most convenient path. It explores its full parameter space, including corners that feel uncomfortable to our intuitions. By studying such extremes, we learn not only about black holes, but about the early universe itself, about how structure formed, and about the flexibility built into physical law. In the end, the story remains deliberately unfinished. The explanations are plausible, but provisional. The evidence is compelling, but incomplete. TON 618 keeps its secrets not because they are unknowable, but because the tools required to fully reveal them are still being built. That ongoing uncertainty is not a flaw in the narrative. It is the reason the narrative continues at all. We return, but everything feels different now. The object ahead is no longer an abstract idea or a distant point of light. It has presence. Even from far away, its influence announces itself, not through sound or motion, but through. Radiation space around us is no longer empty. It is saturated with energy. Long before we reach the central regions, the radiation field becomes intense. Invisible to human eyes, high-energy photons flood the space around the black hole. Ultraviolet light strips electrons from atoms. X-rays penetrate matter with ease, carrying enough energy to disrupt molecular bonds. Without shielding, no biological system could survive here for long. This is not heat in the ordinary sense, but exposure, a constant bombardment of energy. Released by matter falling inward at unimaginable speeds. As we move closer, the brightness grows steadily, not explosively. The light does not flare and fade like a star-going supernova. It is persistent, overwhelming in its consistency. There is something unsettling about that steadiness. This is not a momentary outburst. It is a sustained state maintained year after year, century after century. As matter continues to spiral toward oblivion, time itself begins to behave strangely. At first, the effect is subtle. Clocks near the black hole tick slightly more slowly than those far away. This is gravitational time dilation, a direct consequence of general relativity. Gravity does not just pull on matter, it reshapes time. The deeper we descend into the gravitational well, the more pronounced the effect becomes. From our perspective, nothing feels unusual. Our thoughts proceed normally. Our sense of motion remains smooth. But if we could look back toward the distant universe, we would see external time accelerating. Distant galaxies would appear to evolve more quickly, their motions subtly sped up relative to our own. We are slipping out of sync with the rest of the cosmos, not by choice, but by proximity. Visually, the scene ahead becomes increasingly distorted. The black hole does not appear as a simple dark circle. Its gravity bends light, pulling it into curved paths. Photons that would have traveled past us now arc inward, redirected by the warping of spacetime. This effect, known as gravitational lensing, reshapes everything we see. Light from behind the black hole is bent around it, forming rings and arcs. Portions of the accretion disk that should be hidden from view become visible. Their light wrapped around the black hole and delivered to our eyes along multiple paths. We are seeing the same region from different angles simultaneously, a visual contradiction made possible by curved space. The accretion disk itself resolves into structure. It is no longer a uniform glow. The outer regions appear dimmer and redder, cooler by comparison, though still far hotter than any star's surface. Moving inward, colors shift toward white and blue as temperatures climb. Closer still, the disk radiates fiercely in ultraviolet and X-ray wavelengths, invisible but inferred from their effects. The disk is not symmetric. One side appears dramatically brighter than the other. This is not because it produces more energy, but because of motion. Portions of the disk are rotating toward us at relativistic speeds, while the opposite side moves away. Light from the approaching side is compressed and intensified, an effect known as relativistic beaming. The receding side appears dimmer, its light stretched and weakened. This imbalance creates a sense of motion, even in a still image. The disk looks alive, dynamic, as if caught mid-spin. The brightness difference is not subtle. It is a reminder that velocities here approach a significant fraction of the speed of light. At these speeds, classical intuition fails. Relativity becomes not a correction, but the dominant rule. As we descend further, the sense of scale becomes difficult to hold. The black hole's event horizon does not look like a surface or boundary. It appears as a dark region, a shadow against the luminous chaos around it. This shadow is larger than the physical event horizon itself, magnified by the bending of light. It marks the region from which no information escapes, a visual absence defined by geometry rather than matter. Around this shadow lies the photon sphere, a region where light itself can orbit the black hole. Photons skim along curved paths, trapped temporarily before either escaping or falling inward. This produces a bright, narrow ring encircling the darkness, a sharp contrast between utter absence and extreme brilliance. The sight is unsettling, precisely because it feels so final. Radiation intensity continues to rise. The flux passing through each square meter of space here exceeds anything experienced near stars. The environment becomes actively hostile, not through violence or turbulence, but through sheer energy density. Space itself feels charged. It's filled with interactions invisible to the eye, but relentless in effect as we approach the innermost stable orbits. Motion becomes dizzying. Material here circles the black hole in hours or days, completing orbits faster than planets complete years. Small disturbances grow rapidly. A slight fluctuation sends matter spiraling inward, crossing the point of no return. These final orbits are the most energetic, releasing the last and brightest bursts of radiation before disappearance. Fear emerges here, but it is controlled, intellectual rather than instinctive. There is no sudden threat, no dramatic impact. The danger is embedded in the environment. It is the knowledge that every physical law is being pushed to its extreme. That escape routes are narrowing, that options are vanishing. Time dilation becomes pronounced. From the perspective of a distant observer, our approach would appear to slow dramatically. Motions would stretch out, becoming increasingly drawn out as we near the horizon. But from our own perspective, time flows normally. This asymmetry creates one of the most counterintuitive aspects of black hole physics. Reality depends on where you are standing, or in this case, falling. Visual distortion intensifies further. The universe behind us compresses into a smaller and smaller region of the sky. Light from all directions is bent forward, concentrating into a bright patch directly opposite the black hole. It is as if the rest of the cosmos is being squeezed into a shrinking window, while the darkness ahead expands, soundless, frictionless. The descent feels calm despite the violence implied by the physics. There's no sensation of speed, no rush. Of air, motion through curved spacetime does not feel like motion at all. The only cues come from sight and knowledge, from understanding what the equations predict even when the senses remain quiet. This calm is perhaps the most unsettling aspect. The environment is lethal, the energy is extreme, yet the experience is smooth. Gravity does not announce itself with noise or turbulence. It simply shapes the path forward, indifferent to intent or resistance as we draw nearer to the event horizon. The accretion disk fills much of our view. The bright ring of light wraps around the darkness, distorted into shapes that seem to defy geometry. The black hole's presence dominates perception. Everything else feels secondary, peripheral, reduced. This is the peak of cinematic escalation. The journey that began with distant points of light has led here, to a place where the universe's most abstract principles become visually tangible. Space bends, time stretches, light curves. Motion becomes relative in the most literal sense. And yet, even now, nothing dramatic happens. There is no explosion, no collapse of sensation. The black hole does not roar or pulse. It simply exists, exerting its influence with quiet certainty. The fear it inspires comes not from chaos, but from inevitability. Standing at the edge of this extreme environment, one realizes that the universe is not built for comfort or intuition. It is built from rules that operate consistently, even when their consequences feel alien. Near the black hole, those rules are laid bare, stripped of the approximations that make every day reality feel familiar. The journey has brought us to a place where physics is no longer an abstraction. It is visible, immersive, and absolute. And as we hover on the brink of the point of no return, the final question is no longer about brightness or mass or growth. It is about what happens next when the last familiar reference points dissolve and the universe's deepest boundaries are crossed. Boundaries are crossed. The bound-out ceremony. There is no wall, no surface, no sudden jolt to announce its presence. The event horizon is not something you collide with. It is something you cross. One moment, escape is still theoretically possible. The next, it is not. Nothing about the local environment marks the transition. Physics does not raise a flag. The universe does not pause to acknowledge what has happened. That quietness is precisely what makes it unsettling. From our own perspective, nothing dramatic occurs at the instant of crossing. Space feels continuous. Time continues to flow. The equations of general relativity predict no singular experience at the horizon itself, especially for a black hole of this size. In fact, the larger the black hole, the gentler the immediate conditions at its edge. Tidal forces, the stretching effects of gravity, are relatively weak here compared to those near smaller black holes. If one were relying solely on sensation, it would be easy to miss the moment entirely. And yet, something fundamental has changed. The geometry of space-time has rearranged itself so completely that all possible paths forward now lead deeper inward. This is not a matter of speed or choice. Even light, the fastest thing in the universe, can no longer find a trajectory that leads outward. Every future direction points toward the center. The event horizon is not a location in space so much as a boundary in time. Beyond it, the future inevitably involves the singularity. From the perspective of a distant observer, the story looks very different. To them, crossing the horizon never quite happens. As we approach it, our motion appears to slow, our image stretching and dimming as light struggles to escape the deepening gravitational well. Signals take longer and longer to reach the outside universe. Redshift drains their energy. Eventually, communication fades away entirely. The crossing becomes an asymptote, forever approached but never observed. This split in perspectives is not an illusion. It is a consequence of relativity. Reality depends on where you are. There is no single universal account that captures both experiences at once. Inside and outside disagree, and neither is wrong. That disagreement itself is a clue that we are entering a regime where intuition fails. Once beyond the horizon, the environment begins to change more rapidly. Tidal forces grow stronger as we move inward. Gravity is no longer uniform across the body. The pull on the feet becomes measurably stronger than the pull on the head. This differential acceleration is what produces the phenomenon known as spaghettification, a term that sounds almost playful but describes a deeply violent process. At first, the stretching is subtle. Muscles, bones, and structures experience stress along one direction while being compressed along others. As the distance to the center decreases, these forces intensify. Matter is pulled into long, thin shapes, elongated by gravity's gradient. The process is not explosive. It is gradual and relentless, governed by equations rather than chaos for an ultramassive black hole. This stretching unfolds over a longer distance and time than it would near a stellar mass black hole. That scale does not make it survivable, but it does make it more comprehensible. The violence is spread out, not concentrated into a sudden catastrophe. The body is not torn apart instantly. Instead, it is steadily deformed, its structure overwhelmed by forces that no material can resist indefinitely as the descent continues. Temperatures and energies rise, not because of heat in the traditional sense, but because of motion through curved spacetime. Particles accelerate. Interactions become more energetic. The distinction between separate objects begins to blur as structures are stretched and compressed beyond recognition. Atomic bonds cannot withstand the stress. Molecules disintegrate. Atoms themselves are pulled apart. Eventually, even subatomic particles lose their individuality. The concept of a solid object ceases to apply. What remains is a stream of energy, and matter falling inward, following trajectories dictated purely by gravity. There is no resistance, no friction to slow the fall. Nothing left to hold formed ahead lies the singularity, a region where the known laws of physics predict infinite density and curvature. It is important to be precise here. The singularity is not a place in the usual sense. It is a breakdown in our mathematical description of space-time. When equations yield infinities, it is not because infinity has been physically achieved, but because the framework being used is no longer sufficient. General relativity, our best theory of gravity, works extraordinarily well across an enormous range of conditions. It predicts the behavior of planets, stars, galaxies, and black holes with remarkable accuracy. But at the singularity, it stops making meaningful predictions. Space-time curvature becomes infinite. Time and space lose their distinct roles. Cause and effect, as normally understood, unravel. This is where mystery replaces spectacle. There is no agreed-upon picture of what actually exists at the center of a black hole. Some theories suggest that quantum effects become dominant, preventing true infinities from forming. Others propose exotic states of matter or connections to other regions of spacetime. None of these ideas have been tested. None are confirmed. The singularity remains a question mark at the heart of our understanding. What is certain is that classical descriptions fail. The smooth fabric of spacetime that general relativity describes becomes shredded at the smallest scales. Quantum mechanics, which governs particles and forces at microscopic levels, has not yet been successfully unified with gravity in this regime. The two pillars of modern physics disagree precisely where conditions are most extreme. As we approach this boundary of knowledge, familiar concepts dissolve. Distance loses meaning. Time behaves erratically. The idea of a trajectory, of a path through space, becomes ill-defined. There is no longer a clear distinction between past and future in the way we experience it elsewhere. Everything points inward, not just spatially, but causally. Fear here is not rooted in immediate danger, but in conceptual collapse. The mind seeks patterns, explanations, continuity. Near the singularity, those anchors fail. There is no clear narrative of what happens next because our theories do not extend that far. The universe has led us to a point where it stops answering questions in a language we understand. This is the true climax of the journey. Not destruction, but uncertainty. Not spectacle, but limits. The black hole does not reveal a hidden mechanism or a dramatic secret at its core. Instead, it exposes the edges of human knowledge. It marks a place where our best descriptions of reality no longer apply. Inside the horizon, information about the outside universe becomes inaccessible. Light from distant stars cannot reach us. Signals sent outward never arrive. The cosmos we came from is effectively gone, not because it has ceased to exist, but because the structure of space-time no longer allows interaction with it. The universe has narrowed to a single direction and a single outcome. And yet, even here, the black hole is not malevolent. It does not act with intent. It follows the same laws that govern falling apples and orbiting planets extended to an extreme. The terror it evokes comes from indifference, from the realization that the universe does not soften its rules for observers. As we near the point where our descriptions end, it becomes clear that the black hole is not simply an object. It is a boundary between what can be known and what cannot, at least with our current tools. It is a reminder that physical law, as powerful as it is, has domains where it remains incomplete. This does not diminish science. It defines its frontier. Every era has had phenomena that resisted explanation, not because they were mystical, but because the framework to understand them had not yet been built. Black holes occupy that role today. They are not failures of physics, but invitations to extend it. The approach to the singularity is therefore not an ending in the traditional sense. It is a handoff from known theory to unanswered question. What happens beyond is not something we can narrate honestly without speculation. The universe does not provide a final image or a definitive event. It simply stops telling us what comes. Next, that silence is profound. After a journey that began with distant points of light and escalated through scales of mass, energy, and time, we arrive at a place where the universe withdraws its explanations. The black hole does not resolve into clarity. It resolves into absence. In that absence lies both fear and fascination. Fear, because the familiar rules no longer apply. Fascination, because the universe has revealed a place where it's deepest. Structure is still unknown. The singularity is not just a destination. It is a reminder that there are still questions large enough to humble our most powerful theories. And so the journey reaches its limit. Not with an answer, but with a boundary. Beyond this point, language, mathematics, and intuition falter. The universe has shown us how far our understanding extends, and no farther. What lies beyond remains unspoken, not because it is empty, but because we do not yet know how to listen. We do not yet know how to listen. When we finally pull back from the edge, the universe slowly regains its familiar proportions. Though familiar no longer means what it once did. The black hole recedes, not because it has become smaller or less important, but because perspective has widened. What remains is not an image, but an understanding shaped by everything encountered along the way. Objects like Ton 618 force, a revaluation of cosmic evolution itself. They tell us that the universe was not a slow, gentle place in its youth. It was efficient, aggressive, and capable of assembling extremes very early on. Structure did not always emerge patiently over tens of billions of years. Under the right conditions, gravity worked quickly. drawing matter together into engines of astonishing scale while the cosmos was still young. This reframes how we think about the timeline of the universe. The familiar story often emphasizes gradual buildup. Small fluctuations grow into galaxies, galaxies mature, stars form, planets follow, and life eventually appears. That story is broadly correct, but objects like this remind us that there were parallel narratives unfolding at the same time. While some regions evolved quietly, others raced ahead, creating giants that would dominate their surroundings for billions of years. There is a subtle but important shift that happens here. The universe stops feeling like a backdrop designed to host places like Earth. Instead, Earth becomes one brief outcome of a much larger process. The cosmos is not structured around habitability, comfort, or even longevity. It is structured around physical law. And those laws permit outcomes far more extreme than anything required for life to exist. This realization does not diminish human significance. It changes its nature. We are not central by position or scale, but by perspective. We are among the few arrangements of matter capable of looking back across billions of years and reconstructing a story from faint, ancient light. The fact that we can even speak meaningfully about objects like Ton 618 is itself extraordinary. There is also humility in recognizing how much remains unknown. For all the sophistication of modern physics, for all the precision of telescopes and simulations, black holes still guard their deepest secrets. We understand their effects with remarkable accuracy, yet their cores remain opaque to theory. They sit at the intersection of gravity, quantum mechanics, and cosmology, precisely where our current frameworks fail to merge cleanly. That failure is not a dead end. It is a signpost. Historically, the most productive periods in science have followed moments when existing theories could no longer comfortably explain extreme observations. Black holes now occupy that role. They are not anomalies to be dismissed, but guides pointing toward deeper principles yet to be uncovered. Future observatories are already beginning to extend our reach. New space-based telescopes peer deeper into the infrared, revealing the earliest galaxies and the environments that nurtured the first quasars. X-ray instruments probe the innermost regions of accretion disks with increasing precision. Radio arrays map jets and magnetic structures on scales spanning entire galaxies. Each wavelength adds a new layer to the picture. Gravitational wave detectors promise an even more profound shift. By listening to ripples in space-time itself, they allow us to observe black hole mergers directly, without relying on light at all. These signals carry information from regions that electromagnetic radiation cannot escape. As sensitivity improves, such detectors may one day reveal the growth history of black holes across cosmic time, testing theories that are currently only speculative. And yet, even with all this progress, some questions may remain permanently open. The nature of singularities, the ultimate fate of information. The unification of gravity with quantum mechanics, these are not problems guaranteed to yield to observation alone. They may require conceptual revolutions as significant as relativity or quantum theory once were. There is value in accepting that possibility. A universe with no remaining mysteries would be smaller, not larger. It would imply that reality had been fully compressed into human understanding, that there was nothing left to surprise us. Objects like Ton 618 ensure that this is not the case. They keep the horizon of knowledge ahead of us, not behind. On a more personal level, such extremes quietly reshape identity. It becomes harder to view humanity as separate from the cosmos when the same laws that govern our bodies also govern black holes. The atoms that make up thought and memory obey the same equations that dictate the motion of galaxies. There is continuity rather than division, even across staggering differences in scale. At the same time, the contrast sharpens appreciation for the conditions we inhabit. The calm, stable environment of Earth is not the universe's default state. It is a rare pocket of order within a reality that often operates at violent extremes. Recognizing this does not make our existence fragile in a discouraging way. It makes it precious in a factual one. The black hole also challenges the way we think about power. In human terms, power is associated with action, force, and dominance. In cosmic terms, power often manifests as persistence. TON 618 does not explode or conquer. It shines steadily, converting matter into energy with quiet efficiency over immense spans of time. Its influence is not theatrical, but absolute. This kind of power is indifferent. It does not react to observers. It does not respond to meaning. It simply follows physical law. And that indifference is part of what makes the universe feel so vast. Nothing about TON 618 exists for us. Its light reaches us incidentally, crossing billions of years of expanding space before intersecting our instruments and our curiosity. Yet from that incidental intersection comes understanding. The photons that left the quasar long before Earth existed now end their journey inside telescopes, sensors, and ultimately, minds. In that moment, the universe becomes aware of itself in a small but meaningful way. Matter that once fell toward a black hole contributes, indirectly, to reflection and insight. This is perhaps the quiet resolution of the journey. Not an answer to every question, but a recognition of relationship. The universe produces extremes. Some of those extremes erase structure and overwhelm intuition. Others, like consciousness, allow structure to be recognized at all. Both arise from the same underlying rules. TON 618 does not threaten humanity by its size or power. It does not diminish us by comparison. Instead, it expands the context in which humanity exists. It reminds us that reality is larger, older, and more capable than everyday experience suggests. And it shows that understanding does not require proximity or dominance, only patience and attention. As we zoom all the way back out, past galaxies and voids, past the limits of observation, the black hole becomes one data point among many. An extreme one, but still part of a coherent whole. The universe is not defined by any single object, no matter how massive. It is defined by the relationships between objects, by patterns repeated across scale, by laws applied without exception. In that sense, the story does not end at the black hole. It loops outward again, into ongoing research, into future discoveries, into questions not yet formulated. Each generation inherits a universe that is partially understood and partially mysterious. Objects like this ensure that balance persists. The final impression is not fear, but awe, tempered by clarity. The cosmos is capable of producing things far beyond our intuitive limits, and it does so without hesitation. At the same time, it allows those things to be studied, measured, and contemplated by minds that evolved on a small planet orbiting an ordinary star. That contrast is not a contradiction. It is the defining feature of our place in the universe. We are small, but not insignificant, limited, but not excluded, surrounded by mystery, but capable of understanding pieces of it. And so, after traveling from Earth to the edge of a black hole larger than our entire solar system, the lasting effect is not disorientation, but perspective. The universe feels less like a collection of distant objects and more like a continuous, evolving system of which we are a part. The black hole remains where it has always been, shining from the distant past, indifferent to being known. What changes is not it, but us. We carry forward a slightly altered understanding of scale, time, and possibility. In a universe that allows such extremes to exist, curiosity is not a luxury. It is how meaning is found at all.